Now let's see how an AM wave looks like. Here this sine wave shows the data signal, that is VM, that is message signal or modulating signal, whose maximum amplitude is capital VM. The signal is represented with small vm and maximum value is VM. Its frequency is FM as we know, and it is the carrier signal VC with maximum amplitude VC, whose frequency is FC. Here from this image you can see that this carrier signal have the highest frequency and this is a low frequency signal. Now as we said, the amplitude modulated signal is a signal whose amplitude, where the amplitude of the carrier signal will change in according to the modulating signal. While writing that equation, we write that the AM signal is equal to this VC plus this data signal into sin omega CT. That is, the resulting signal VAM should have frequency this one and its amplitude will change like this data signal changes. Then we can draw the signal as let us consider initially the data signal amplitude was 0. Then the carrier signal will remain the same. It will look like the same. Now from here onwards the amplitude of data signal is increasing. Then the amplitude of carrier signal will increase and the maximum value will occur when the maximum value of data signal reaches. So we can draw this like here. This curve shows this data signal. നിങ്ങൾക്ക് എളുപ്പത്തിന് എന്ത് ചെയ്യാം, വേണമെങ്കിൽ ഈ ഡേറ്റ സിഗ്നൽ ഇവിടെ ആദ്യം വരച്ച് വെക്കാം. ഒരു ഡോട്ടഡ് ലൈനിട്ട് വേണമെങ്കിൽ എന്ത് ചെയ്യാം, നമുക്കത് വരച്ച് വെക്കാനായിട്ട് പറ്റും. അതായത് ഈ സെയിം സിഗ്നൽ തന്നെ എനിക്ക് എന്ത് ചെയ്യാം, താഴത്തേക്ക് വരയ്ക്കാം. When the amplitude will become minimum, then here also it will become minimum, nearly 0. Then again as the amplitude increases, this will also increase like this. But the frequency of the signal is the same. Actually this dotted line is not there. The signal is like this. This is the signal. When the amplitude of data signal is maximum, the amplitude of this AM signal will also become maximum. When the amplitude of data signal will become minimum, its amplitude also will become minimum. When the data signal is 0, its amplitude is VC, because we are adding the data to this carrier signal VC. Now we can write this amplitude is VC, this is 0, this is minus VC, and this amplitude is VM, because this much amplitude is VM. The same amplitude will repeat here, and if there is a minimum value exists there, then we can say that this is V minimum. This will happen only if, because you can see this is the 0 axis, this is VC, and if VM is less than VC, for example this amplitude is 5 volt and this is 4 volt, then this V minimum will become equal to 1 volt. If both VM and VC is equal to 5 volt, this V minimum will become equal to 0 because we are adding the data to this VC. When VC equal to 5 and VM equal to minus 5, 5 plus minus 5 will cancel out and this will touch this 0 axis. If this carrier signal is 5 volt and this is minus 4 volt, the V minimum will become 1 volt. So we can say this is equal to minus of VC, that is the maximum amplitude, plus Vm sin omega m into t, and the maximum amplitude is Vc plus Vm sin omega m into t. Now from figure, this is V maximum and this is V minimum. Then V maximum minus V minimum will give 2 Vm. Why? Because this is V maximum, this is Vm, and this is also from 0, this is also Vm, and this is V minimum. Then V max minus V minimum will give you 2 Vm, that is Vm is equal to V max minus V minimum by 2. Now what is VC? VC is V minimum plus this is Vm. This is Vm, this is also Vm, and this much is VC. This is VC, this is Vm, this is V minimum. Then VC is equal to V max minus Vm. Now how this equation comes? Because VC is this much, this is V max, and this much is Vm. So this VC is equal to this V max minus this Vm. Now we can write VC is equal to V max minus Vm is already we know, V max minus V minimum by 2, which is equal to V max plus V minimum by 2. Now we have two equations, one for Vm and another one is for Vc. Now what is the modulation index of AM signal? Ma is equal to Vm by Vc. We know the equation of Vm and equation of Vc, which is equal to Vmax minus Vmin by this 2 and this 2 will cancel out, Vmax plus V minimum. So this equation is also important because we can find out modulation index Ma if we know both Vmax and V minimum. This can be obtained from this figure. അപ്പോൾ ഈ ഫിഗർ നിങ്ങൾ വരച്ച് നോക്കുക, വരച്ച് നോക്കുമ്പോൾ നിങ്ങൾക്ക് ഈ ഇക്വേഷൻ എഴുതിയത് മനസ്സിലാവും. എന്നിട്ട് ഡൗട്ട് ഉണ്ടെങ്കിൽ ചോദിക്കാം. Now we have to find the power relations in AM wave. AM waveലെ power relations ആണ് നമുക്ക് അറിയേണ്ടത്. As we already discussed, the AM wave consists of three components. First one is carrier, next one is lower sideband, and third one is upper sideband, where the carrier wave is Vc sin omega ct with maximum amplitude Vc. Both upper sideband and lower sideband have maximum amplitude Ma Vc by 2. This we already discussed. Now we can write the power in AM signal. PAM is equal to the equation of power equal to V square by R. Different equations are there. Here we know the maximum amplitude. Then we can find the power in terms of voltage and resistor. Then we can write voltage of carrier square divided by R, that is V square R, plus voltage of lower sideband square by R plus voltage of upper sideband square by R, where all these voltages are RMS voltage. We need RMS voltage, but these voltages are the maximum value. Then we can find the Vrms is equal to the maximum voltage divided by root 2. Then how we can write this? The total power of AM signal PAM is equal to V carrier is maximum amplitude by root 2 the whole square. So here it is Vc. So Vc by root 2 the whole square divided by R. Why? We need V square by R, where V is RMS. RMS equal to this by root 2 plus Ma Vc by 2 by root 2 the whole square by R, plus here also in the upper sideband the maximum amplitude is Ma Vc by 2, so its RMS value is by root 2. So Ma Vc by 2 by root 2 whole square by R. Now we can write this as Vc by root 2 the whole square is Vc square by 2R plus Ma square Vc square by 2 square is 4. 4 into root 2 square is 2. So it will become 8 into R. Here also plus Ma square Vc square by 8R. Now we can take Vc square by 2R as common, then which is equal to Vc square by 2R into 1 plus here Ma square by 4 plus Ma square by 4. Here Ma square by 4 plus Ma square by 4 is equal to Vc square by 2R into 1 plus Ma square by 2. So Vc square by 2R is Vc by root 2 by R the whole square, where Vc by root 2 is the carrier signal maximum amplitude by root 2. That is, this is the power of the carrier signal. You can see here the maximum amplitude of carrier is Vc. Its RMS value is Vc by root 2. That Vc by root 2 the whole square by R. So actually this term is the power of carrier signal. So we can write it as Pc into 1 plus Ma square by 2. So the power of AM signal is equal to power of carrier into 1 plus modulation index the whole square by 2. This equation is very important when we will do the problems. So in this equation for AM, when m is equal to 1, then the equation will become PAM is equal to PC into 1 plus, when m equal to 1, ma square is equal to 1, that is 1 by 2, that is equal to 1.5 PC, where ma equal to 1 is its maximum value. So the maximum value of power that we can achieve without distortion is 1.5 PC. So this is maximum power. This you can derive from this equation. Next, we have to find the current relations in AM. Now, we derived this equation of PAM equal to PC into 1 plus MA square by 2 by using the equation V square by R. Power is equal to V square by R. Now, we can also write this equation or the power as, we can rewrite this equation as PAM by PC is equal to 1 plus MA square by 2. We can write the power equation as P equal to I square R. Okay, I square R. There is another equation V square by R. We used this equation to derive the power of AM. Now we can replace this PAM and PC with this equation, that is equal to I T square R by IC square R, where IC is the current due to the carrier and IT is the current due to AM signal. AM signal is a signal which we are going to transmit after modulation. That is why the total current IT is, I is represented as IT, where T stands for total current. That is, AM signal consists of carrier, upper sideband and lower sideband. So the corresponding current is IT. Then we can write IT by IC is equal to root of 1 plus m square by 2 using this square. Now which is equal to, that is IT is equal to IC into root of 1 plus m square by 2. So this is the equation for current in AM. All these equations we can derive from basic equation of AM. First we have to study the basic AM equation. From that AM equation we know the three components: carrier, upper and lower sideband. Using that three components we can find the total power using V square by R. Now we can find the current components. So next let us consider the case of modulation of a carrier by several sine waves. That means we are using one carrier signal and more than one sine waves, that is sine wave or data signal. There may be so many data signal which we can represent as VM1, VM2, etc. And there is only one carrier signal is there for modulation. Then such case, what will be the total voltage and how its power varies, all these can we have to discuss. Now let V1, V2, V3 etc. be the modulating voltage, modulating signal voltage. Then the total modulating voltage, that is the total voltage we have to transmit, is equal to Vt is equal to root of V1 square plus V2 square plus etc. That is, we have to transmit V1, V2 etc. up to Vn, then the total voltage we have to transmit through this carrier is equal to root of V1 square plus V2 square plus etc. up to Vn square. Now let's divide this equation by Vc, that is carrier signal voltage. Vt by Vc is equal to, now let us take capital Vt and capital Vc, then which is equal to V1, this is capital V1 square by Vc square plus V2 square by Vc square plus etc. Why we took Vt by Vc? Because modulation, the equation for modulation index Ma equal to Vm by Vc, where Vm is the maximum voltage of the data signal to be transmitted and Vc is the voltage of the carrier signal, and this is the data, this is the carrier. Here also we are going to find out modulation index, where Vt is the signal to be transmitted, that is total signal to be transmitted, and Vc is the carrier signal. Then the equation will be like this. Now Vt by Vc can be represented as total modulation index Mt, because this is not a single signal. There are so many data signal to be transmitted, then the total modulation index Mt is equal to root of V1 by Vc, means first data signal voltage maximum. V1 is maximum amplitude of first data signal divided by carrier. Then it is modulation index of the first signal, that is M1 square plus M2 square plus etc. That is why we took the maximum amplitude or capital V. Small letter V represent the signal and capital letter V represent the maximum voltage. So this is the equation for total modulation index in case of modulation by several sine waves. There may be problems based on this equation. Now we already derived the equation for AM signal. PAM is equal to PC into 1 plus m square by 2. This we know already, but here it is equal to, sorry, we can write it like PC plus PC into m square by 2. But here m is the total modulation index, which is equal to root of m1 square plus m2 square plus etc. Then we can write PAM is equal to PC plus PC into m square is, the root will go, then m1 square plus m2 square plus m3 square plus etc. by 2, which is equal to PC plus PC m1 square by 2 plus PC m2 square by 2 plus etc. So in modulation by several sine waves, the power of the carrier will remain the same and the power of the side bands, these all are side bands. While deriving the equation for AM signal, we saw that an AM signal by single modulation, that is modulation by single sine wave, consists of three components: a carrier wave, upper sideband and lower sideband. Here you can see it consists of the carrier signal as such, and then there are several sidebands are there. Carrier wave will remain get unaffected, and the sideband power will be the sum of individual sideband powers. So just remember this equation also. Now let us consider the equation for AM with more than one sine waves. We already discussed the modulation by several sine waves modulation index and total power. Now let us see how we can write the equation for modulation by several sine waves. Here we can write the carrier signal is equal to Vc sine omega c t. Here this we already know. Now let us consider there are several modulating signal Vm1, Vm1 of t, Vm2 of t, Vm3 of t, etc. Then we can write Vm1 of t is equal to V1 sine omega m1 t and Vm2 of t equal to V2 sine omega m2 t, etc. Similarly, this is V1, this is second signal V2 and sine omega m1 t, here sine omega m2 t. Similarly, we can write any number of data signal. Then VAM is equal to, as we know in case of AM, we are modulating the amplitude of carrier only and frequency will remain same. Then the amplitude will change as Vc plus data signal. Here there is so many data signals are there, that is V1 sine omega m1t plus V2 sine omega m2t plus etc. into sine omega ct. Why the sine omega ct? Because the frequency will remain same. This is the total amplitude. Amplitude will change with respect to data signal. Now we are going to take this Vc common. Then we can write Vc into 1 plus here V1 by Vc. What is V1 by Vc? V1 by Vc is M1. So we can write M1 sine omega M1t plus M2 sine omega M2t plus etc. into sine omega ct. Now we can write Vc into sine omega ct as Vc, that is the carrier signal. So we can write small letter Vc into 1 plus m1 sine omega m1 into t plus m2 sine omega m2 into t plus etc. Don't confused with capital V and small v. Capital Vc into sin omega ct is small vc. This is the carrier signal. From this equation also we can see it consists of one carrier wave, that is Vc, and so many sideband, because it will go like m1 sin omega m1 into t, m2 sin omega m2 into t, etc. Now you can do in another ways. You can multiply, and in that case you can multiply Vc and sin omega ct into this equation. Then we will get sin A sin V, sin A sin V, and you can expand it. Since it is a long equation, we write it like this. So the next topic is vector representation of AM. Before going to that, we know that if there is only one carrier signal and only one modulating signal, the modulated signal, that is AM signal, consists of three parts. First one is carrier, next one is upper sideband, and third one is lower sideband. It consists of the three components. Now then the total signal is the sum of the total phasor representation is the sum of, or the total vector is the sum of the carrier or vector addition of this carrier, lower upper sideband and lower sideband frequencies. That is, for a single frequency modulating signal, Single frequency modulation means only one data signal or modulating signal is there. So for a single frequency modulating signal, the AM signal envelope is produced from vector addition of carrier upper sideband and lower sideband. Now these two sideband frequencies will combine and produce a resultant component which will combines with the carrier. Let's see how this will happen. So the carrier have frequency Fc. Upper sideband is with Fc plus Fm and this is with Fc minus Fm. Then the angular frequency will be omega c plus omega m and omega c minus omega m. These are the angular frequencies. Now the resultant signal is the vector addition of first frequency component is omega c. Now to this omega c plus m and omega c minus m will get added. Now these two components have a phase difference. So this is omega lower sideband and this is omega upper side band. These are the three frequency components. This is the carrier signal, this is the lower sideband signal, that is this one, and this is the upper sideband signal with omega c plus omega m. Then the total or the resultant will be like this, because these two lower sideband and upper sideband are in this direction, and if we draw parallelogram we can see that the resultant will be like this. Here the vector addition will happens, that is the resultant frequency component will be the vector addition of the carrier lower sideband and upper sideband. Now let's see how the signal looks like. While drawing the waveform for AM, we saw that the AM signal will look like this. In the top portion there will be one sideband, and here it will look like one data signal, and here the other data signal. This is only the dotted line, and the carrier wave will exist here like this. Now we have to know about the vector addition of the signals. Now here when data signal is equal to 0, that is when the modulating signal is equal to 0, there will be no modulation. Then the carrier signal will remain as the same, that is the data signal, the upper sideband will be like this and lower sideband will be in this direction. So the vector addition is 0. There exists only carrier signal when the data signal is 0. Now as the amplitude of data signal increases, there will be modulating signal. Then there is a lower sideband, there is an upper sideband, and as a resultant there will be a component. Now at the peak point, all this is the carrier signal, this is lower sideband, this is upper sideband, all these will get added and the resultant will be the maximum. Similarly again, when the amplitude decreases, this will be the carrier, this is lower sideband, this is upper sideband, and this will be the resultant signal, and this will go. And here when data signal is equal to 0, again the lower and upper sidebands will be like this. In the negative direction also, here this is the carrier, this is lower sideband, this one is upper sideband, and the resultant will be like this. And this is how the vector addition of these three frequency components will happen. Now you can see the maximum positive amplitude of this envelope. We will call these two portions as envelope. Envelope means in the carrier signal we are placing envelope of data. So we can see the maximum positive amplitude of this envelope occurs when both the carrier upper and lower sideband frequencies are its maximum positive value at the same time, because all these three components have its maximum value at the same time. That is, this V maximum can be written as Vc plus V upper sideband plus V lower sideband frequency. Similarly, the minimum positive value will occur at positive amplitude of this envelope occur when the carrier is at its maximum and upper and lower sideband frequencies are its minimum value. That is V minimum, that is positive minimum and positive maximum. This is equal to Vc minus V upper sideband frequency minus V lower sideband frequency. Then only when the minimum will happen. Similarly, we can write the negative maximum also. The negative maximum occurs when all these are its negative maximum, that is minus Vc minus V upper sideband minus V lower side band. Similarly, you can write minus V minimum also. This is how we will represent the AM wave in vector representation.